the receiver has to select the prime numbers. So the attacker in a way that the attacker should not predict the prime numbers. Okay, so but it is a trivial task selecting the prime numbers. The again, so the receiver has to select the large prime numbers instead of small prime numbers. The receiver has to select the large prime numbers so that it will be unpredictable. The factorization will be, because attacker will have only the product of two prime numbers. So the factorization will be should be complex. Okay, so in that manner, the receiver has to select two prime numbers. Large prime numbers should be selected. So how can a receiver can select two large prime numbers? Is first of all, whatever the number the receiver is selecting, whether it is a prime or not. So generally, all prime numbers are odd numbers except two. Remaining all are the odd numbers. Suppose if receiver selects one prime number, one odd number. So first of all, some number. Suppose receiver selects some number like this. 7525759 is one number. So whether it is a prime or not, it is an odd number, but specifying whether it is a prime or not, again, it is, if for large numbers, it is a trivial task. Then how can we test whether it is a prime number or not? So again, so after selecting the prime number, first receiver has to apply the primality test by different types of primality test algorithms are there, right? Miller-Rabin is there, Fermat's primality test theorem or Fermat's Rittel theorem test is there. So using any of the probability primality test theorems or deterministic algorithms, so receiver has to select two prime numbers. So that is a trivial task. So generally, the entire data will be converted to the binary format, right? So whatever the size we are going to take to store the prime numbers, so whether it may be 512 bits data, or one can assign the 1024 bits data for a prime number. So maximum bits allocated to a prime number, one prime number is 512 bits. Then whatever the memory allocated, so here we need to choose one prime number. So with the 512 bits, 512 bits, and by applying the primality test. So that is one of the issue with the RSA algorithm. Selecting the prime numbers, large prime numbers itself is one big issue. And so once it is selected, for encryption and decryption, so for encryption, we need to calculate that is C is equals to m power e mod n. So here, if e value is a larger value, again, large value. So e value will also be the selected integer, and the plain text. Plain text is, suppose if there are two prime numbers, two prime numbers, like large prime numbers are there, the product of two prime numbers become more large, right? Then whatever the plain text we are going to choose, that will that should be less than the n. But if the plain text is also a large number and e value is also large number, so computing this m power e, computing m power e or c power d is also a trivial task. Okay, it is also one of the issue in the RSA algorithm. Okay, it is computationally hard to find m power e or the c power d value. Okay. So choosing the prime numbers as well as the computing the m power e and the c power d values is the trivial task in the RSA algorithm. Then how can we calculate this m power e or c power d values? Is simply we need to So simply in order to calculate, suppose if there is a number like a power m, if we want to calculate a power m, the thing is we have to do the m into m minus 1 number of multiplications, okay, with the same a into a into a into and so on, m minus 1 number of multiplications. So generally we are going to use the binary representation, isn't it? We are going to use the binary representation. So whatever the number is the a power m, so the power value should be represented with the binary value, okay, the power value should be represented with the binary value, like b0 to b1 b2 binary values, like suppose if the number of bits in m is k bits, if m consists of k bits, then we need to represent m is equals to 0 bk to b0, so where b0 is the lsb and bk is the most significant bit, msb. Then so we need to write this we need to write this m as b0 plus b1 b1 into 2 power 1 plus b2 into 2 power 2 and so on, bk into 2 power k, okay, bk into 2 power k. So we need to multiply with the powers of 2. Simply we need to take the summation of bi 2 power I, bi 2 power I, that is I is equals to 0 to k. Okay, so if bi, the corresponding bit is 0, suppose if m is equals to 5, okay, if m is equals to 5 means 101. So 101 means, so b0 will be 1 and b1 will be 0 and b2 will be 1. So how can we represent 1 into b0, so b0 plus b1 into 2 power 1 plus b2 into 2 square. So b0 is 1 plus b1, b1 means 0, so 0 into something is 0 plus b2, that is 1, 1 into 2 power 2, like this we need to specify. Okay, so here we have to take the summation of, that is m can be represented as m is equals to the summation of 2 power I, okay, where bi is not is equals to 0, okay. Sorry, summation of bi into 2i, where bi is not is equals to 0, bi is not is equals to 0. So that is the procedure for calculating the a power m, that is in the case in RSA we'll calculate m power e and the c power d. So this is one procedure for calculating that. And selecting the prime numbers again, so just by using the primality test, by applying the primality test algorithms we can select. Okay, or we can also use a method called square and multiply algorithm in order to calculate m power e or c power d. So that is, if we want to calculate a power m value, we can use a method called square and multiply algorithm. So that's the same thing. So what we discussed now, let us go with PPT. Is the computational aspects of RSA algorithm. So as I said, the complexity of the computation requires two aspects. One is the key generation process. Key generation is nothing but key. RSA key consists of 5 parts. That is P, Q, E, N, and D. So these are the all 5 parts of the key. So encryption and decryption procedure. So in encryption, we'll calculate m power e, and in decryption, we'll calculate the c power d. So these are the computational aspects. Okay, so encryption and decryption involve raising a large integer to a large integer. That is m power e. That is m power e. So exponentiation will require the more computation if it is having the large values. Okay. See, so how can we calculate some m power e value? So in order to calculate, so we have to do the repeated multiplications, or we can simply perform. Suppose if x power 16 is there, we can write first, we can calculate x square whole square, again square, like that. Okay, x square whole square, again whole square, like that we can calculate. So that is one procedure. The other procedure is simply if a power m is there, so whatever the exponentiation is there, so we need to convert that as a binary number, represent that as a binary number, and then we need to represent from b0 to bk, and then we need to take the whatever the 0. So binary value will contain zeros and ones. So only we need to take the product of the product of the ones, not the zero values. So this procedure is called as the square and multiply algorithm. So the square and multiply algorithm. So in order to compute that, in order to compute a power m mod n. So in RSA, C is equals to m power e mod n for encryption, and for decryption m is equals to c power d mod n. So we can use this square and multiply algorithm. That is, if z is equals to 1 for I is equals to k down to 0, means k to 0. So we need to write, we can write it as z is equals to z square mod n. So if bi is equals to 1, then we need to take the multiplication, z is equals to z into a mod n. See, this is the example. If n is equals to this value and m is equals to this and a is equals to, mean a power m mod n, a power m mod n. So that is, a is 9726, power 3533, mod n is 11,413. So how can we do that? Is simply we need to take m bits, convert 3533 to bits. So it requires total 12 bits, 0 to 11. Okay, 0 to 11. So 3533 can be written as the binary representation is this one, 110, this one. Okay, 110, 111, 00, 1101 is the value of 3533. Then we need to write in this manner, and then 1 square into the power, 1 square into the base value, and again, so the base square into this value. Mod, okay, we need to do the mod operation. So at every step, so 2659 square into mod n. So 2659 square will get some value, right? Then we perform mod 11413. So by performing the mod with the 11,413, we'll get the result 5634. At every step, we need to do the mod. Okay, we need to take the mod value, and then we need to take the sum of all these values. See, so if b is equals to 1, then we need to take this value. If it is 0, then no need to take. If you observe in step, so z is equals to z square mod n. If bi is 1, then we need to take z is equals to z into a mod n. So that is why wherever b value is 1, wherever bi value is 1, there it is multiplied with a. Otherwise, it is not. Simply, it is going to take the square and mod with n, square with mod with n. So this is for bi is equals to 0. If it is 1, if bi is equals to 1, then only it is going to multiply with a. So this is one of the procedures for calculating the power, a power m mod n, square and multiply algorithm. So the key generation we'll see in the next class. So this is about the RSA. So all of you practice some problems on RSA. Any doubts? Okay, if no doubts, you can leave. Thank you.